So Prashanjit, I have 45 minutes, right?
Yes.
Okay, good.
45 to 50, roughly. There is a so Professor Kumarshan has raised hand.
I just wanted to say hello to Saugato.
Hello, sir. How are you?
I'm quite fine. How are you?
Fine, fine, fine. Thank you, sir.
Yeah.
Good to hear from you. Yeah.
Yeah, I just came in because I have another meeting. I am the one who organized. Okay.
Okay, sir. Yeah.
Take care. Bye.
Bye.
Hello, Shogotoda.
Hey, Moushami, how are you?
I'm good. How are you?
Good, good. Thank you. Thank you. And how is Onup and your daughter?
Yeah, everyone is fine.
Good, good.
In Aizer, Kolkata, how is the situation there?
Better, I think. So since this is not in city, so as far as the COVID is concerned, we are better off till now.
Okay.
Okay.
And you are staying inside the campus, right? No?
Yes, yes, very much inside.
And inside the campus, I mean, the things are all fine, no?
Till now, we have been fortunate. There hasn't been a single case till now.
Okay, so that's good then.
Okay, so can we start now? Okay. Okay. So on behalf of the organizers, a very warm welcome to Professor Shogoto Bandyopadhyay and to all the participants of webinar on PDE and related areas. We are honored to have Professor Shogoto Bandyopadhyay with us today. Professor Bandyopadhyay obtained his doctoral degree under the guidance of Professor Bernard Decaronia in 2007 from École Polytechnique Fédérale de Lausanne. His research interest lies in the nonlinear analysis of differential forms with emphasis on the existence and regularity issues in pullback equations, minimization of functionals involving differential forms, and differential inclusions involving the exterior derivative operator. He is in Aizer, Kolkata since 2008, and today he will speak on the equation gradient of U transpose H of U, gradient of U equals G. Shogoto, the platform is all yours now.
Okay, thank you, Prashanjit. So I thank the organizers for the kind invitation. I mean, during these difficult times, organizing a webinar on a scale as large as this is really a commendable feat. And so I'm happy to be a part of this great initiative. So thanks again. So as Prashanjit said, so I'm going to speak on this equation, transpose of the gradient of u times h composed with u times gradient of u is equal to g. So let us, so this is, so this talk is based on an ongoing project with Bernard Dakaronia, Vladimir Medvedev, and Mark Troyanov. So basically, what I'm going to speak of, about is the following. So our objective is as follows. So let n be a natural number, n is greater than or equal to 2, and omega is an open subset of Rn, and gh be two matrix valued functions of appropriate regularity. So we are interested in the existence of a diffeomorphism u that is defined in omega and is a diffeomorphism onto its image with regularity depending on that of g and h, satisfying this PDE transpose of the gradient of u times h composed with u times gradient of u is equal to g in omega. And we shall consider this PDE with additional boundary conditions such as Dirichlet boundary condition or Dirichlet-Neumann boundary condition. So before we start describing the results and its consequences, so let us see why is this PDE relevant. So this equation comes in geometry in a very natural way. So this PDE can be seen as a problem of equivalence of certain geometric objects up to a change of coordinates. For example, the skew symmetric case, that is when h and g are skew symmetric, studying this PDE is equivalent to asking if two differential two forms are equivalent up to a change of coordinates. In the symmetric case, when GH are symmetric and positive definite, this equation naturally arises in Riemannian geometry as the equivalence of Riemannian matrix. In particular, when H is identity, this equation comes up in nonlinear elasticity because in that case, the left-hand side, which is a transpose of gradient of u times gradient of u, is referred as a right Cauchy-Green tensor, and in which case we refer the PDE as an equation with prescribed right Cauchy-Green tensor. So, so having seen the relevance, now what we do now is we're going to see, so we're going to describe the results that we have obtained in this context, and the structure of the talk would be as follows. So we'll start with the studying the algebraic problem, that is, how does this PDE look in its algebraic setup. We will see this algebraically. This is related to a very famous problem in linear algebra. Then you move on to PDE, and in PDE we'll consider two cases, namely the skew symmetric case and the symmetric case. While the focus of this talk is a symmetric case, so this is where our ongoing project with Dakaronia, Medvedev, and Troyanov comes in. We shall start by talking about skew symmetric case for two reasons. First reason being that with the skew, then we can understand the difference between these two cases. And the second thing is this: it is with the skew symmetric cases that we are introduced in this area. So basically, we'll start by briefly recalling the skew symmetric case, the results of which are somewhat old. But anyways, we won't spend much time on skew symmetric case other than recalling its results. Then we move on to symmetric case, where we will where the results are new and I believe is of current interest. So having said this, so let's move on to the algebraic case. So algebraically, the problem is as follows. So let n stands for the dimension of the space and AB be two n by n matrices. We are interested in the existence of an invertible matrix X that satisfies X transpose AX is equal to B. So if there is such an invertible matrix, we say that A, B are congruent. So studying the congruence classes of matrix is quite an important problem in linear algebra, and there are many results in this direction out of which we will mention two very famous ones. So first result appears in the symmetric case, which says that two symmetric matrices are congruent if and only if they have the same signature. This is famously known as the Sylvester law of inertia. And the second case being the skew symmetric case, when two skew symmetric matrices are congruent if and only if they have the same rank. This is known as the Leuviel theorem. So you see this, the skew symmetric case is somewhat more flexible than the symmetric case. So the question that comes up now is what happens in the general case. So in the general case, while there are many results, there are no result that can be stated as simply as in the cases of symmetric case and skew symmetric cases. So we won't get into that. So except referring to this article by Lancaster-Rodman, canonical forms for symmetric, skew symmetric, real matrix pairs under strict equivalence and congruence, which appeared in linear algebra applications in 2005. Okay, so all that is fine. So this we will see the connection of congruence of matrices in the PDE. But what we specifically need is that that we will need to solve, we will need to consider this congruence problem with an additional constraint. So what are those constraints? Let's see. So constraint problem. So let n stand for the dimension of space, n greater than or equal to 2, nu be a unit vector, and let A, G, H be three non-singular matrices with G, H symmetric, and let epsilon be equal to plus minus 1. So epsilon will stand for the sign of certain quantity, as we will see later. Then there exists a non-singular matrix phi satisfying phi transpose H phi is equal to G, epsilon times determinant of phi greater than 0, and phi x is equal to ax for all vectors x perpendicular to nu. So if and only if, okay, so before I say, tell you the conditions, you see this, why we are saying it constraint, because we are adding more constraints on phi. That is, we want the determinant of phi to have a prescribed sign. This is the first, this condition. And the second condition being that we are specifying the action of phi on an n-1 dimensional subspace. So we are adding two extra conditions on phi. That's why we refer to it as constraint congruence problem. If and only if the inner product of gx with y is same as the inner product of hax with ay for all xy perpendicular to nu, determinant of g, determinant of h, they have the same sign when G inverse nu and A inverse, H inverse, the transpose of A inverse nu are perpendicular to nu, this condition, this technical condition is satisfied. So it's an if and only if condition. Furthermore, more importantly, phi whenever it exists is unique. So you see this, so if you start with, so you start with a GH where you do not have this condition, then third condition you don't need to check. Maybe another side remark is that these two quantities, as G inverse nu and A inverse H inverse A, the transpose of A inverse nu inner product with nu, these two quantities either simultaneously 0 or they're simultaneously non-zero. This can be proved. And phi whenever exists is unique. So in the subsequent discussion, we shall denote phi by C with epsilon as superscript, nu as subscript, and GH semicolon A. Okay, so in our case of this problem with this algebraic result will play important role when we will study the Dirichlet problem. There we will see epsilon will stand for the sign of the Jacobian determinant of some function, and A will depend on the boundary value. You will see this. But to be able to use this theorem in the Dirichlet problem, what we need is a functional version of this theorem. That is, what do you mean by that? Where A, G, H will be matrix valued functions defined on the boundary of omega with prescribed regularity. And then you want, if A, G, H has certain regularity, the phi that we obtain here, does it have the required regularity. So this is answered in the next theorem. So now, okay, n as usual depends on the dimension of the space. R stands for the degree of regularity, and okay, epsilon stands for sign. But now omega is open with CR plus 1 boundary, and A, G, H are are three functions defined over omega, over the boundary of omega, of regularity CR be non-degenerate. By non-degenerate, we mean that at each point, on boundary point, AX, GX, and HX are invertible matrices. That is, AX, GX, and HX are invertible matrices for all X in the boundary point. With GH, symmetric means GX and HX at each point, boundary point, they are symmetric matrices, satisfying this usual hypothesis. I don't get into that again because it's the same hypothesis that appeared in the previous theorem with but now these hypotheses are pointwise, so satisfied at each boundary point. So if these three conditions hold, then the function now C epsilon nu, the function that the quantity that we have defined in the previous theorem, which is a function defined on the boundary now, is also a CR. It's a function of regularity CR. So if A, G, H are CR functions, then phi that you obtained in the previous theorem is also a CR, a function of with regularity CR. So that's about the algebraic problem. Now we move on to PDE. So as you said, in the PDE case, in the PDE case, we consider two cases: the skew symmetric case and the symmetric case. While the focus of this talk is a symmetric case, we shall start with a skew symmetric case, and we will recall one result. This okay. So, but let me spend a slide or two on the skew symmetric case now. In the skew symmetric case, the first thing that we observe is this: that identifying skew symmetric matrices with exterior two forms, the problem can be reformulated into a problem of differential two forms. That's something. Then the problem becomes that given two differential two forms, when can you say if those two forms are equivalent up to one change of coordinates? Now, this is a very classical problem in geometry. Now, this problem for the locally, this problem for the case of closed non-degenerate two forms was first solved by Darboux, I think sometime during 1880 or 1886, when he proved that every closed non-degenerate two form is locally equivalent to the standard symplectic form. And the global problem was first, I think, was first asked by Paley sometime during 1950s, and then Moser answered the question for volume forms in 1965. And while solving this problem, Moser introduced a method, a very powerful method, now known as Moser's flow method. So I will just make some comments on Moser's flow method, which become later very powerful because a whole lot of problems can be solved by this. For example, other than solving the problem of volume forms, one can solve Poincaré lemma, Moore's lemma. So several of these big theorems follow from Moser's flow method. Anyway, so how does the method look like? Let's see. So in Moser's flow method, one considers the ODE, ddt of phi t is equal to ut phi t for all t lying between 0 and 1 and x in omega, and find 0x is x, where we choose ut in such a way that phi 1, which is the flow at times t is equal to 1, phi 1 satisfies our PD, that is the transfer of gradient of phi 1 times h of phi 1 times gradient of phi 1 is equal to g in omega. So the question is, how does one consider derivative d alpha t is equal to minus d dt of ht, and the interior product of ht with ut is alpha t, where ht is a closed homotopy joining g to h, that is hr ht is 0. Once if you can show that that the phi t star ht has time derivative 0, then phi 1 star h1 is equal to phi 0 star h0. Phi 0 anyway is assumed to be an identity function. H0 is g, so therefore phi 1 star h is equal to g. So that's easy to see. But then how does one prove that ddt of phi t star ht is 0? It is a standard exercise by using Lie derivative formula and Cartan's magic formula. This can be seen in any differential geometry book, so we shall skip it for the moment. But as powerful as the Moses flow method is, it has one weakness, is that it doesn't give solutions with improved regularity. To gain regularity, Moses flow method needs to be combined with a suitable fixed point method or some subtle regularization. And when we do all that, what we arrive at is at the following theorem. So it's a pretty old theorem, but we recall it nonetheless, because this theorem will help us compare the situation between the symmetric case and the skew symmetric case later. Let n be a natural number, nr be two natural numbers with n greater than 2 be even. Alpha is something that lies between 0 and 1, and omega be a bounded and smooth domain. Let GH be two non-degenerate closed differential two forms with CR alpha regularity in the interior and CR plus 1 alpha regularity on the boundary. Then there exists a diffeomorphism of omega bar of class CR plus 1 alpha satisfying our PDE with identity of the boundary if G minus H is orthogonal to the space of harmonic forms with vanishing tangential component. The tangential component of G is equal to the tangential component of H, and then TH plus 1 minus TG has full rank for all T in 0, 1. Okay, now just a couple of hypotheses, because regarding the hypothesis, we are assuming n to be even because we want these forms to be non-degenerate. And okay, and you see, anyway, so the thing is, now about these three conditions, you see the first condition is turns out to be necessary as well, because this is because of this the homotopy invariance of Deram cohomology. This first thing follows, and the second thing is necessary because U is identity on the boundary. What is not necessary is a third condition. Now, because we are assuming that we have a linear non-degenerate homotopy. Now, that need not be true all the time, but finding a non-degenerate homotopy, non-degenerate symplectic homotopy that respects the boundary condition is quite difficult, and there may be subtle topological obstructions that we don't understand at this point. So anyway, so these are the so that is the results that I want to talk about in the skew symmetric case. Now, so before I move on to the symmetric case, just one maybe comment that I want to mention here is this. So one can prove similar global results in a degenerate case as well. By degenerate, we mean that when G then GH don't have the full rank, but in this case, usually we could not prove there is in general we could not prove any improvement of regularity. Then one usually gets solution which is just as regular as GH. So with this, so that's the skew symmetric case, the result in a skew symmetric case I wanted to talk about. Now we move on to the symmetric case now. So in the symmetric case, okay, so we start with some definitions. So let n be a natural number, omega be an open set, and G be a symmetric non-degenerate, so be a matrix valued function that is symmetric and non-degenerate. By that we mean that the transpose of G is G, and G of X is invertible at each X in omega. So we define what is called Christoffel symbols of second kind. Now what are those? So for each I, j, k, 1 to n, we define this quantity, the gamma, with k in the superscript and ij in the subscript is this quantity half. Then with gkp, kp in the superscript, this superscript means we're considering the kpth element of G inverse. Okay, so G inverse means Gx is inverse. Okay, then time multiplied by del I GJP plus del J GIP minus del P GIJ in omega. So when you say that this is a crystal symbols of second kind, so naturally the question that comes to our mind is whether there is a crystal symbol of first kind. But indeed there is one such, but we won't mention it here because it won't be any use to us in this talk. So once we have the crystal symbols, what do we do with it? We will define many n by n matrices, what are called crystal matrices. This we define as follows. So we define these many n by n matrices, gamma 1, gamma 2, gamma n, okay, where the ijth entry of gamma k is the gamma with I in the superscript and kj in the subscript in omega. It is now how does one remember this? You see, the one way of remembering is this. If the ijth entry of gamma k is this, is that you just interchange I and k. So when you interchange I and k, you get the definition of gamma with I in the superscript and kj in the subscript. So this is what we have as many n by n matrices that we refer as crystal matrices. Now, what do we do with crystal matrices? With this, we do all this to define a very important quantity that will be very important to us. Is we define what is called Riemann curvature tensor. What is that? So when G is C2, the Riemann curvature tensor is a two form defined as this one, 2 d gamma plus gamma wedge gamma, where gamma is this one form that is summing of I to 1 to 1, 1 to n, gamma I dxi is a Leuviel. So this quantity is called a Leuviel connection of G. So you see there's some point here is this, we are viewing this gamma as a one form over the space of matrices. So d gamma is a two form and gamma with gamma is also a two form, and this is non-zero even though gamma is a one form, because now we are on matrix multiplication is non-commutative. So this thing doesn't get killed off as it happens with general usual forms. So this is what we call the Riemann curvature tensor. But you say, and why do we need G is C2 here? Because crystal symbols already has one derivative in it, and now then we take another exterior derivative. So we're differentiating twice. So G is usually assumed to be C2. Okay. But so since we'll be doing PDE, so we want to assume as least regularity as possible. So we want to have the notion of Riemann curvature tensor when G is C1. And since we will be considering the case, only the case when the Riemann curvature tensor is 0, what we want to have the notion of zero Riemann curvature for C1 matrix valued functions, non-degenerate matrix valued functions. So how does one do that? So we do it in the usual way, namely we multiply the test function and throw the derivative on the test function. Here test function will be matrix valued test function. When G is C1, we interpret the condition Rg is equal to 0 in the weak sense as follows. So let n be a natural number, omega open. So G now is C1 value, so is a symmetric and non-degenerate matrix valued function of regularity C1. We say that G has 0 Riemann curvature if for all ij, when you look at the integral of psi, the psi times gamma I gamma j minus gamma j gamma I plus del j psi gamma I minus del I psi gamma j is 0 for all matrix valued test functions, then we say that G has Riemann curvature 0 Riemann curvature tensor. This is essentially what you do is you look at this coordinate wise, you look at the ijth component of this quantity, you then multiply test function from the left hand side, and then you throw the derivative wherever you can on the test function, on the matrix value test function, and you get this definition. Okay, so with this we are all set. Now let's get to the PDE. So it all started with this following theorem. which is known as fundamental theorem in Riemannian geometry. Let n r be two natural numbers, n greater than or equal to 2, omega be open, bounded, and simply connected. Let G be symmetric and positive definite with regularity CR. Then for every triple x naught in omega, small c naught in Rn, capital C naught in GLNR, invertible matrices, there exists an immersion of U of class CR plus 1, satisfying this equation that the transpose of gradient of U times gradient of U is equal to G in omega, Ux naught is equal to C naught, and gradient of Ux naught is equal to capital C naught, if and only if Gx naught is a multiplicative symmetrization of capital C naught and G has zero Riemann curvature. Furthermore, the solution of 1, if exists, is unique. Now, in the books, so usually you won't see this in this form. So for example, in Spivak's books, when you look at this theorem, what you will see is a local version, but that is largely a cosmetic difference, because what we assumed here is a simply connectedness. So in a simply connected domain, it's easy to upgrade the local result to a global one. But what is non-trivial is a case is R is equal to 1k, case where the Riemann curvature tensor is to be interpreted in the weak sense. So this version, okay, a version similar to this can be found in the CLS book, linear and nonlinear functionality with applications. But of course, CLA considered the case R greater than or equal to 2. Now, R is equal to 1 case, which is a non-trivial generalization, was done by Hartmann and Wintner in this article on the fundamental equations of differential geometry that appeared in American Journal of Mathematics in 1950. So for us, this problem in the symmetry case started with this theorem, because when we looked at the theorem, the first question that came to our mind, so okay, what happens? Well, so what's about the boundary? So what about the analogs, the boundary value problems? And the first thing, what about the analog? So what about the boundary value problem? The second thing, can we do away with the positive definite case? That is, what about the pseudo-Riemannian case? So now, what I'm going to tell about, so I'm going to tell you 3 results that we obtained in this direction. So we'll start with the easy case, that is the Dirichlet problem. So this is the easy case. So what is the theorem is this: let nr be two natural numbers and omega be open bounded simply connected with connected Lipschitz boundary. Let H be an n by n matrix with the symmetric part is invertible. So whenever there is this subscript S, we mean that we are looking at a symmetric part. So we are assuming the symmetric part of H to be invertible, and let G be a matrix valued function of class CR with the symmetric part of G non-degenerate. Let phi be an immersion of class CR plus 1, and let gamma denote the Leuviel with a connection of the symmetric part of G, which we consider because we have assumed GS to be non-degenerate. Then there exists a function U of class CR plus 1 satisfying this equation, our equation, transfer of gradient of U times H times gradient of U is equal to G in omega. U is phi on the boundary of omega, and gradient of U is equal to gradient of phi. So this means, this equivalent, this means we are posing the Dirichlet condition and Neumann boundary condition at the same time, if and only if the symmetric part of G has Riemann curvature tensor 0, dGA is equal to gamma transpose GA plus GA times gamma in omega. Now here, okay, I have to tell you something. So this, in other words, this means that the covariant derivative of GA is 0. Now here, one needs to, now in the previously, in the skew, when we studied skew symmetry case, we said that we are identifying a skew symmetric matrix as a 2 form, okay? But in this case, what we are seeing is this, we are seeing this matrix GA as a 0 form over the space of matrices. So this is a difference between the skew symmetric case and the symmetric case. So the second condition can also be restated as saying that the GA has zero covariant derivative. G evaluated for some boundary point x naught, G of x naught is equal to the transpose of the gradient of phi at x naught times h times gradient of phi at x naught. And fourth condition is the extended derivative of gradient of phi minus gradient of phi times gamma wedged with nu is zero almost everywhere with respect to the n-1 dimensional house of measure on the boundary. Furthermore, the solution, if exists, is unique and lies in a and is a diffeomorphism of omega bar with image phi of omega bar of class CR plus 1 if phi is a diffeomorphism onto its image of class CR plus 1. So here just a point, since we have assumed the boundary to be Lipschitz, so normal vector exists almost everywhere with respect to the n-1 dimension house of measure, and that's why we have this condition and in the fourth hypothesis. And again, the gradient of phi is assumed to be a zero form over the space of matrices, and the extended derivative is to be calculated accordingly. So that's about the Dirichlet problem. Okay. And okay, now we move on to the Dirichlet problem. Okay, so we will give you two theorems in Dirichlet problem, one on Lipschitz domain and another on smooth domain. Now the question is, so usually the common sense says that once you have a theorem for Lipschitz domain, it should automatically applicable for smooth domain, but you will see this. The theorem on Lipschitz domain is unsatisfactory in one respect, and that part is one can alleviate in the smooth boundary case. So we'll start with the theorem on the Lipschitz domain. So with the usual hypothesis that omega be open, bounded, simply connected, and Lipschitz with connected boundary. Let H be a matrix, n by n matrix, with a symmetric part invertible. G be a CR valued, G be a matrix valued function of regularity CR with a symmetric part non-degenerate. Phi is an immersion, and let gamma be the Leuviel connection of the symmetric part of G. Then there exists U satisfying this Dirichlet problem. Now V is phi on omega, on the boundary for omega. There is if and only if the Riemann curvature tensor of the symmetric part of G is 0. The covariant derivative of GA, the antisymmetric part of G, is 0, and there exists a non-degenerate phi of class of regularity CR. By non-degenerate we mean the determinant of phi is non-zero at each boundary point, satisfying that the transpose of phi x naught times h times phi x naught is equal to gx naught for some x naught, some boundary point x naught, and phi wedged with nu is equal to the gradient of the boundary value wedged with nu, and d phi minus phi gamma wedged with nu is 0 almost everywhere with respect to the n-1 dimensional house of measure on the boundary. Furthermore, the solution when exists is unique, and the solution is a diffeomorphism of class CR plus 1 onto phi of omega bar when phi is a diffeomorphism of class CR plus 1 onto its image. So that is a theorem in Lipschitz domain. But you see this, there is something unsatisfactory about this theorem, being that it doesn't tell you what, so how does one construct phi? So it is not clear how does, so how does one construct phi? Now this is something, so one can, so we can solve, so this problem one can solve when domain is more regular. That is, when omega is smooth, we can give an explicit candidate for phi, and that's which will solve the Dirichlet problem in a satisfactory way when the domain has more regularity. And this is about, and this is what the next theorem is about. Okay, so now we are assuming the domain to be open, bounded, simply connected. Is all the same as before, but now with regularity CR plus 1 regularity. H is as usual as in the previous case. H is n by matrix with the symmetric part invertible. G is same as before. G is same regularity CR with the symmetric part is being non-degenerate, and phi is an immersion of class CR plus 1. When there exists a U satisfying the Dirichlet problem, if and only if the Riemann curvature tensor of the symmetric part of GS is 0, okay, as usual, GS and HS, their determinants have the same sign, and then GS and gradient of phi transpose HS gradient of phi, they induce the same first fundamental form on the tangent space. And then we have this technical condition, which I am not stating, there's no point in stating this now. And the fifth one is that d c epsilon nu minus c epsilon nu times gamma wedged with nu is 0 on the boundary of omega, where epsilon is sign of determinant or sign of the Jacobian determinant of the boundary value. The antisymmetric part of GA has 0 covariant derivative. And we have this, I'm sorry, I think there is a question. Should I take it now or later? Okay. So maybe I take it later. So, and so I see there is a question, but we need the phi to be an immersion, so that so we cannot take phi to be 0. I mean, our take, maybe I shall, okay, we shall come back to the we shall come to this question later. And the transpose of C epsilon nu transpose HA, C epsilon nu is GA at the boundary point x0. Furthermore, the solution when exists is unique and satisfies this Dirichlet Neumann boundary condition that U is phi and gradient of U is equal to C epsilon nu on the boundary of omega, and the usual condition. So you see, so the difference between the Lipschitz boundary situation and this smooth situation is this, that the C epsilon nu is the one that appears in the constraint congruence problem in the algebraic situation. And the reason that we cannot use in the Lipschitz boundary case, because C epsilon nu doesn't have the right regularity in the Lipschitz boundary case. However, it will have a right, because you see the phi needs to be at least CR. So the C epsilon nu doesn't have this regularity when the domain has regularity less than CR plus 1. So this, but when the domain is at least CR plus 1 regular, one can one can use our algebraic techniques, and that will give us the candidate for phi here. So while this theorem might look a little heavy, so let's look at a very special case. So let's go back to the classical case, the problem with which we started, namely this. So namely this problem that the transfer of gradient of U is equal to gradient of U is equal to G in omega, and U is identical on the boundary if and only if the Riemann curvature tensor of G is 0, gradient of G is positive, sorry, the determinant of G is positive, G in this G and our standard matrix, they have the same first fundamental form, and we define this quantity B, which is of class CR, defined as I plus G nu minus nu times inner product G nu with nu plus nu is square root of G, tensor with nu satisfies dB minus B gamma wedged with nu is 0 on the boundary. Furthermore, the solution, if exists, is unique and is a diffeomorphism of omega bar of class CR plus 1. So this is the problem that we started with, and so this is the analog of the fundamental theorem of Riemannian geometry in the context of boundary value problem. Now, before I finish, I will start. Maybe I have some time, so maybe I will give you a 2-minute proof of this theorem, a sketch of this proof, a sketch of the proof. So we'll prove this theorem in 3 steps. So in the first step, what we do is we solve a global Frobenius type theorem. So in the first step, we find a matrix valued function of class CR that satisfying df is equal to f gamma in omega and f is equal to b on the boundary of omega. Now this equation is solvable because the G has 0 Riemann curvature and dB minus B gamma wedged with nu is 0 on the boundary. So this is the this is this is a non-trivial part of the proof. So first we solve this equation to have an f that is matrix valued function. The next part is easy. What we do is now we solve a prescribed gradient equation. We find a u of class CR plus 1 satisfying this problem. Gradient of u is equal to f in omega and u is identity of the boundary. This equation is solvable because each row of fi, each row of f has 0 curl. This is because of certain symmetry properties of Levi-Cevita connection or Christoffel matrices. And then we have this equality of tangential component on the boundary. So once we do that, the final step is we show that f transpose f is equal to G in omega. Now this is because both f transpose f and G satisfies this equation dx is equal to gamma transpose x plus x gamma in omega, and x is G on the boundary. So once we do this, you see we are solved because f transpose f is G, so we replace f with gradient of u. So clearly u solves the equation. So with these 3 steps, so one can solve this equation. Now, before I finish, maybe let us just summarize what we have seen. The symmetric and skew symmetric cases difference. So in the symmetric case, there is uniqueness of solution. The solution has always been unique, while in the skew symmetric case, we have strong non-uniqueness. The symmetric case is elliptic. This leads to uniqueness and straightforward regularity results in the symmetric case. However, the skew symmetric case is non-elliptic and the regularity issues are much more involved and there is strong non-uniqueness. And the surprising thing about symmetric case is that the symmetric case, in spite of being a nonlinear problem, decouples into 2 linear problems. You see here, step 1 and step 2 decouples into 2 linear problems. This is not the case in the skew symmetric case. But one thing maybe before I finish, I should tell you why we are considering why we are telling this case a symmetric case, because we are, you see, we are not assuming H and G to be symmetric, but nonetheless, we are referring these theorems as symmetric case because we are assuming there's an invertibility of H's and G's. That means that while we can assume the antisymmetric parts to be 0, in which case you do not have to consider the hypothesis corresponding to antisymmetric parts, one can never assume we cannot never remove the symmetric parts. So the invertibility of symmetric parts play a crucial role in our argument, and that's why we are referring it as symmetry cases. So with this comment, maybe I'll stop here. Thank you. So, so do I have to, so how does the question and such session proceed?
Sorry. Thanks, Professor. Sorry, I was muted, so you could not hear me. So thank you very much for this wonderful talk. So we have got some questions in our question and answer box. So should I read it out for you?
So are they still live? I mean, they can ask me. Can they ask me directly, or
If you want, I will try that.
Yeah, because I see I've shown in this question, phi must be you there.
Yeah, so I'm asking him to talk.
Yeah.
Hello, Swarnendu. Hello, Swarnendu.
Yeah, hi. Yeah, you can hear me?
Yes, Swarnendu.
Yeah, okay. So yeah, sorry, my question got posted kind of like midway. So I was asking, so when phi is a diffeomorphism, you said U is a diffeomorphism also between domain and the image of phi.
Yes.
But the other solvability condition, does it force that, or is it known like when you must actually be phi? So there are other solvability conditions, right? So
which one you want?
So when is it known that so U has the same boundary picks up the is equal to phi on the boundary,
yes,
kind of, and it's also a diffeomorphism between the image of phi and the domain, right? And phi itself, if phi itself is a diffeomorphism, so the solvability condition, is there anything in the solvability condition that might force that you must be phi? Because you said U is unique, so is anything known when you must actually be phi?
You want, okay, that I haven't thought of. So you want phi in the interior as well?
Yeah, I mean, what I'm trying to say that you said U is unique, right?
U is unique, yes.
So they are, so when phi is a diffeomorphism, phi obviously is defined in the interior. So because if you assume phi is also a diffeomorphism.
Yeah. You see, phi is throughout, so phi is defined on the interior because phi is defined on omega bar.
Yeah, phi is defined on omega bar. But I'm talking about the case when you also assume that phi itself is a diffeomorphism. Then is there like the condition is known when, I mean, U picks up really just phi itself. So phi itself actually has to satisfy the equation. Otherwise, you cannot solve the equation. Is it some condition regarding that is known?
So you see in the you see in the Dirichlet case, for example, phi satisfies the equation on the boundary.
Yes.
And that's trivial.
But does it have to really, like, for example, like satisfy? Because I was wondering, because U is unique, so that's what so if we know if
but phi did not but phi did not satisfy the equation in the interior, but you want a additional condition.
Additional condition which might that U actually has to be phi and phi. I mean,
then probably you need some more condition on phi.
Okay.
You have something. I think so. This is just an off the cuff remark. I have to think about.
Okay, and I had like just another question, that can we do this? So all of this is with like general matrices, right? I mean, I see that there is a sign condition on the diffeomorphism, but can we do like slightly better, like make it, for example, solve in like spatial orthogonal matrices or unitary matrices rather than just in like invertible ones? Like, for example, U taking values in U is a matrix valued functions, but can we?
So you want U to be
values in, let's say, spatial orthogonal group or something.
No, you need. I know. So so one thing is this. Okay, this is, of course, this is known. So let's say in orthogonal, H is identity and G is identity. That's what he was talking about. That is,
I mean, in general, given a G, so is there like conditions when I can solve for U taking values in the, because just with analogy with the Riemannian case, that would mean that U is also an isometry and not just locally transform the Riemannian curvature into the constant coefficient one. Because this, if I understood correctly, this is just like the Riemannian normal coordinates, but the global version with boundary data and everything.
Yes.
And so if U takes values in the orthogonal group or something, then it would be an isometry as well, and not just
then I don't. So if you say, let's say if U gradient of U lies in ON,
Yeah.
then I think there is this Leuviel theorem, right? So when n greater than 3, then if you have higher regularity of U, then U will be affine. So then you have to, I don't remember. So there is this Leuviel theorem, which says that if n greater than equal to 3 and gradient of U lies in ON, and U is even if you take U to be C1, then when n greater than equal to 3, U has to be affine. This is Leuviel theorem. C2 case is a triviality, but so then we have to frame the problem in a different function space.
Okay.
So, for example, there is this paper by this Dacronia, Marcellini, and this Paola someone. They consider this problem one in W1 infinity case. In W1 infinity case, there are infinitely many solutions. But as soon as you become C1, then your solution will be only affine. There's Leuviel theorem.
Okay. I guess the W1 infinity case, you can take the piecewise affine ones.
Yeah.
Like laminates.
So even without boundary condition, I think this I have to speak of the reference, but Leuviel theorem, I can get back to you. When n greater than equal to 3, U is C1, gradient of U lies in ON, then U has to be affine.
Okay. Okay.
Okay.
So
I think maybe I will get the reference and send it to you.
Okay. Okay.
Okay.
Thanks.
Yeah.
Okay. So there is a question by Marina Deschiel, says that in the theorem of Dirichlet boundary condition, is it not sufficient to consider the boundary condition phi equal to 0?
No, that is something that because we need phi to be immersion. For our, we need this immersion means the gradient of phi we want needs to be a full rank, invertible. Okay, so we cannot take gradient of phi to be 0 in our argument.
Okay.
Okay.
So there is another question by, I think this is the same part, by Minmay Bishwas. He says, is it reasonable to consider the problem with regularity in weaker spaces, say Sobolev spaces?
One thing I can do is, I take sufficient p sufficiently high so as to make it an algebra and solve it. So that is, I think, probably you don't have it in mind. But no, when p is small, we have not considered even the solving of this global Frobenius type result. I'm not very clear. Even the linear problem. So when you look at the first step when you're solving this theorem, the first step there is this d of f is f gamma and f is b on the boundary. I don't know how to solve it when p is small. I don't know.
Okay. So now we have a next question from Johannes Osborne. He says, thank you for your great talk. To what extent is the Lipschitz condition necessary in your results?
Well, we are talking about the boundary value problem. So when we show that, so what we do is this normal. So how do you solve this problem? One trick is that we solve it at one point, and then the uniqueness of solution guarantees that we can solve the boundary value problem. That we go from solving at one point to boundary value to solving at a point to solving at a boundary value problem. This transition requires Lipschitzness of the boundary. So in a crucial way. So yes, I think probably unless one sees the proof, it's So basically, we solve it at one point, and the uniqueness says that it actually solves the boundary value problem, and that's where the Lipschitzness argument comes in.
Okay. So I have now a question.
Yes, tell me.
So in this theorem, as it is in the similar question like what Swarnendu was asking, you need H's to be invertible, the symmetric part.
Yes.
So for general matrix, is there some result? Maybe the full theorem is
Okay,
not available,
okay.
but some part
Right.
of it.
It is a very good question. This is precisely actually, okay, so we are working on it now. I mean, we have some results, but what you are talking about, basically the question is, what is the right notion of Riemann curvature for degenerate matrix? Now, there is, when GS is non-degenerate, then clearly then we have this Riemann curvature tensor, whose behavior is well understood, and things are all good. But when the matrix is, when this GS is degenerate, then for degenerate matrix, when you want to define a Riemann curvature tensor, there is I would say there is not one way. I mean, we have 2-3 candidates to start with, and then we saw that, okay, in one theorem one candidate works, in the other theorem it does not work. So there is not one notion that fits all. So yes, so there are some theorems, yes. So this degenerate case is a work in progress. Unlike this one we have already submitted, but degenerate case we are working on it now. I mean there are, it's a completely, it's a different territory, and things are much more subtle.
Okay.
Simply because Riemann curvature tensor is not that well behaved, and first of all there is not one notion, and then it is not as well behaved as in the non-degenerate case. Yeah.
Okay. So I have one more question.
Yes, tell me.
So in this theorem again, generally, I see that U is in CR plus 1.
Yes.
But phi is also in CR plus 1. But is there any phi? That generally we expect one more regularity. To be CR.
No, it's a boundary value. It's like Laplacian of U is equal to F, U is equal to phi on the boundary. So phi will have the same regularity on U, right? In the big boundary. Yeah.
Okay. Okay. So with this.
And okay, maybe one more. So in the stock, we have kept H to be constant all the time. But okay, one can make H is a variable, H of U, because by using the composition properties of fullback. So, but we don't state it here because this will make theorems more complicated, and it's difficult to fit it in one slide. So we assume that H to be constant. Yes. Yes. So, is there any other question?
So, are there any more questions? So, if not, there is a question actually. Something has come up. Oh, yes. So, Shanandu can still talk.
Yes, Shanandu, please. Yeah.
Yeah. So you said just that about the variable coefficient H.
Yes.
But in that case, you need both G and H to have like the curvature 0, right?
Yes.
Yeah. Okay.
Similarly, similarly in the skew symmetry case, when we solve like phi star G is equal to F, we assume G and F to be closed.
Exactly,
so basically, the closeness is what zero Riemann curvature is here.
Yeah, but here it's just like otherwise you cannot pull it right back.
Yeah, of course.
It's impossible.
Yeah.
Theorem agragium. Yeah. So okay, thanks. Yeah.
Okay. So if there are no more questions, let us thank Professor Bandyopadhyay again.
Thank you.
Wonderful talk.
Thank you. Okay.
Now I request. Thank you very much to make this session successful, and we hope to get your participation in future talks as well.
Thank you. My pleasure.
Yeah, for the participants, I would like to repeat this announcement again, that if for some unforeseen problems during the talk or before the meeting starts, please visit our webpage for any unforeseen problems. We will be able to connect you via our webpage. This is just this announcement was just for safety measures. Now I thank all the participants, and we will see you in next 2 days for Professor Siddharth Mishra's talk on deep learning and computations of PDEs. And I request all the participants to leave the platform now. And thank you all.
Thank you. Thank you. So I stop share. Okay.
Thank you, Saurabh.
Thank you. So I mean, so I'll leave, right? So how do I leave? Leave. Okay, I found.
Just leave.
Yeah.
Sorry.
So I'm ending the meeting.